Okay, we are starting kind of a complicated chapter in calculus, and we are talking about solids of revolution, and we're going to talk about two ways to find the volume of these solids of revolution. But first of all, let's talk about what we mean when we are talking about a solid of revolution. Let's look first of all at the graph of y equals the square root of x, or y equals x to the 1/2, starting at x equals 1 and ending at x equals 4. So there's x equals 1. I couldn't get it to start at 0 and just show you that. But here's x equals 1, here's x equals 4, and that's kind of what the area looks like under that curve, the square root of x, or x to the 1/2. So now what we're going to do is we're going to turn this area into a solid, and here's how we're going to do that. We're going to look at it three-dimensionally, first of all. So if I put that graph, that little area, in a box, that's what it would look like. And then what I'm going to do is I'm going to take that area and I'm going to rotate it around the x-axis, kind of revolve it around the x-axis 360 degrees. Okay? And that's what it looks like when you do that. Okay? So you take that area and it's resting on the x-axis, and you basically rotate the whole thing around the x-axis. Okay, and it makes an interesting solid shape, kind of a round shape, as they all will when you revolve a shape around an axis. So our question now is we need to figure out the volume of that solid that we've created. All right, so let's look at how we're going to do that. So let's think back first of all to when we were finding area, which was the very first part of integral calculus or antiderivative calculus. And we were adding up a bunch of rectangles when we did that to approximate the area. And if you remember, the length of each rectangle was whatever f of x was at the time, and it changed for each rectangle. The width was some delta x, some small change in x. And so the area of each rectangle was those two things multiplied together, f of x times delta x. So then we add all of those rectangles up, so we're adding together a bunch of f of x's times delta x's, and that would be the sum of the area of these rectangles. And so we talked about what happened when the width of the rectangle becomes really, really, really small and approaches 0, and the number of rectangles as a result would approach really, really large numbers and would approach infinity. So that's when we change from the sum to the integral. So that e, that sum, that sigma, becomes an integral sign, and then delta x becomes so small that it is instantaneous change in x, and it becomes dx. So that's how we approximated the area. The reason I'm going over that is because we're going to use those same concepts to talk about how we're going to find the volume. So instead of rotating the whole function, what I'm going to do is I'm going to rotate each of these rectangles around this bottom axis here, this bottom line. And so when I do that, what happens is I make little cylinders or discs. So you can kind of see that as each rectangle rotates around its bottom edge, I create kind of a shallow cylinder resting on its side, and some people refer to these as discs because that's kind of what they look like. All right, so let's talk about the measurements of each one. Just like with the rectangle, it had a height of f of x. Well, now f of x is the radius of this cylinder, and delta x, which used to be the width of the rectangle, is now the height of the cylinder. So whatever f of x happens to be at the time, that's the radius, and delta x is the height of the disk. And so we find the volume of those, which you know the volume of a cylinder is pi times r squared times the height. But we replace radius with f of x, and we replace the height with delta x, and we get pi times f of x squared times delta x. Okay? And hopefully you understand that the reason for that is because we are finding the volume of each of these little cylinders, each of these little disks. And I just made a substitution. F of x is your radius, according to the picture, and delta x is your height, according to the picture. All right, and so we add all of those together. That just means there's a sigma in front of it. And then when I change from the sum to the integral, remember what I did before, that sigma becomes the integral sign, and the delta x becomes a dx because it is now an instantaneous change. So that's what I'm looking at right there. And obviously, since pi is a constant, I can pull it out in front. So I have pi times the integral of f of x squared dx. All right? So that's the formula you're going to need to know. You're obviously going to start and stop somewhere, so you're going to have numbers on top and bottom of this integral, but the process is essentially the same. So we are going to go through an example of this. In fact, we're going to do the example that I started with. It's going to be the graph of y equals x to the 1/2 from x equals 1 to x equals 4. All right, there's my formula. It's the same one you just saw. So I know that my f of x is going to be x to the 1/2, so that's what's going to be squared in here. And I know I'm going to be starting at x equals 1 and ending at x equals 4. Okay, so let's just plug that information in. Before I take the antiderivative of this, I do want to simplify what I'm taking the antiderivative of. So x to the 1/2 squared is, I guess I'm going to write it again. And so I simplified, and x to the 1/2 squared is just x. And you'll always want to simplify whatever is in here so that you don't have to do any weird integration stuff. You can just take the antiderivative of a very, very simple function. So I'm taking the antiderivative of x, which is 1/2 x squared, and I'm going to evaluate that at 1 and 4. So if I evaluate that at 4, I get 8. If I evaluate that at 1, I get 0.5. And remember, there's a pi sticking out in front, so that's the constant that I'm going to multiply by at the very end. So my answer is going to be 7.5 pi units cubed. All right, that is the exact area of that shape that you saw spinning around and spinning around. All right, so here's one for you. I want you to rotate the graph of y equals x squared around the x-axis from x equals 1 to x equals 3 and calculate the volume of the resulting solid. So if you're watching this video, pause the video. The entire question is there, and you can resume the video once you think you have found the answer. All right, I'm going to assume that you did this question and you are interested in seeing if your answer matches up. So what we do is we take our f of x, our x squared, and we put it in the integral sign, and we square that. And we are going from x equals 1 to x equals 3. So if I simplify that, that's going to be x to the 4th. You're going to take the antiderivative of x to the 4th from 1 to 3. And you could do this on a calculator if you wanted to, or you could do it by hand. And you should get 242 pi over 5, or 48.4 pi. All right. If you're wondering how I got that answer, I obviously didn't show a lot of steps, but you can ask me, you can email me, or send me a Facebook message, and I can send you clearer steps on how I did that, or we can discuss it in class if you prefer to discuss it in person. All right. Now, what happens if we're not rotating around the x-axis, but we're rotating around some horizontal line, y equals k? Well, it depends, and that would depend even if we were talking about area too. We need to know whether that line is above the function or whether it's below the function. Because whenever we're finding area, there's an upper function and a lower function, and the same is going to be true for when we're finding a volume. So if the line is above the curve or the graph f of x, then we're going to do upper minus lower, the line k minus whatever my f of x is. And if the line is below the graph, then I'm going to do f of x minus k, and I'm going to square that. And looking at these, it probably doesn't matter, because once you square both of those, you're going to get exactly the same thing. So in essence, it doesn't really matter as long as you do subtract f of x and k somehow, and then square that, take the antiderivative of that, and find your volume. All right, so for example, if I had the graph of y equals 4 minus x squared, and I was going from 0 to 2 on the x-axis, but I want to rotate it around the line y equals -1. All right, then find the volume of the resulting solid. I know that my f of x is going to be non-negative. If I plug in any x from 0 to 2, I'm going to get a positive answer, a positive y. which means that it's going to be above y equals -1, meaning that the line y equals -1 is going to be below the entire function. So I'm going to use the f of x minus k version of finding the volume. And again, I really don't think it matters because once you square it, they will both look the same. Okay, so I plug in what I know. My f of x is 4 minus x squared. My k is -1. And so I've got 5 minus x squared. And all of that is being squared. And as I've said before I go and take the antiderivative of this, I need to simplify it as much as possible. I actually need to square this out. Okay, and if I do that, I get 25 minus 10x squared plus x to the 4th. Now I can take the antiderivative term by term. 25, the antiderivative of that is 25x. The antiderivative of 10x squared is 10 over 3 times x to the 3rd. And the antiderivative of x to the 4th is 1/5 x to the 5th. Okay, and then I'm going to evaluate that at x equals 2 and x equals 0 because that's where I started and stopped on the x-axis. And if I do that, this is what I get when I plug in 2, and obviously when I plug in 0, I get zeros everywhere. So it's going to be pi times this, which is going to be 446 pi over 15 units cubed. All right? Now, the washer method is a little bit different, but it's basically the same concept. Let's talk about what a washer is. Anybody that's done any kind of construction or even some assembly of a table that you got from IKEA or something, you've seen what a washer is. But for those that don't know, we'll talk about it. If the area that we're talking about does not rest on the axis of rotation, so every example that we've done up until now, the area it actually stops on the axis of rotation. But that doesn't always happen, so we need to have a plan for that. Okay, so let's say we've got your typical rectangle, but it does not rest on the x-axis, but I still want to rotate around the x-axis. Well, what's that going to look like? It's not going to look like a disk like we had before. Okay, we still have f of x, we still have a delta x, but now we have a g of x, this second function that tells us what the bottom border of the area is. F of x tells us the top border, g of x tells us the bottom border of the area, and delta x just tells us how wide that area is. Okay? So the area, you would find the length of it, which would be f of x minus g of x, and the width would be delta x. So that's how you would find the area. So now if we rotate it about the x-axis, this is what we're looking at. Okay? So you can kind of see what's going on. That's what a washer is. It's basically a disk with a smaller disk cut out of it, or a cylinder with a smaller cylinder cut out of the middle. All right? They have the same center, but they have different radii, or different radiuses, however you want to say it. So the volume would be pi times the bigger radius squared minus pi times the little radius squared, multiplied by the height in each case. So it's the same thing, it's just that we call the bigger radius f of x, and the smaller radius g of x, and we plug those in, and our height is delta x. So instead of pi times big R squared minus little r squared times the height, it's going to be pi times f of x squared minus g of x squared times delta x. And then changing it to the integral, we just put an integral sign there, and dx instead of delta x. All right, so that is a formula you'll want as well. So here's an example. Let's say I'm finding the volume of the solid formed by revolving y equals x to the 1/2 and x squared about the x-axis. So first of all, I need to know where the area is and what it looks like. Okay. So they cross at 0 and they cross at 1, and it looks like root x, or x to the 1/2, is bigger than x squared everywhere between x equals 0 and x equals 1. So my upper boundary, my f of x, is going to be this x to the 1/2, and my lower boundary is going to be my x squared. So that's going to be my g of x. Okay, so here's what they look like. I'm sorry the graph is not very, very accurate. but this curve up here is supposed to be y equals the square root of x, and this one down here is supposed to be y equals x squared. And then there's the area between them. Okay, and we take like a little rectangle that's that has its highest point up here and its lowest point down here, top point being on the graph of y equals root x, bottom edge being on y equals x squared. And we rotate that around the x-axis, and that's the disk that we get. Okay, so remember our f of x was root x, our lower function was x squared, so I square each of those separately, subtract them, don't forget the pi that's out in front, and we are going from 0 to 1. And as I said before, we have to simplify this, so root x squared will be just x, and x squared will be x to the 4th. So that's the integral we're looking at, and then I just take the antiderivative. The antiderivative of x is x squared over 2. The antiderivative of x to the 4th is x to the 5 over 5. So that's the function we're looking at. Now I can plug in 1 and 0. 1 will get me a half minus a fifth. 0 will get me 0 minus 0. So that gives me 3/10 times the pi that was sticking out here. So it's 3 pi over 10 units cubed. And that would be the volume of that solid after it was rotated around the x-axis. And that's it. If you have any questions, feel free to email me, Facebook me, and we will discuss this at the beginning of class tomorrow just to clear up any bad ideas or any confusion that you might have, and we'll do some examples.